In this video, we continue with our discussion of Chapter 21. We left off talking about standard reduction potentials. Here's a table that shows standard reduction potentials for a variety of ionic and elemental species. The species at the top have the largest positive standard reduction potentials. These are the species that are most stable in their reduced form. That means that their oxidized form is the most reactive. They're very good oxidizing agents. So for example, at the top we see F2, fluorine gas, which oxidizes pretty much everything. And it will grab electrons from anything, concrete, water, oxygen, anything, and produce fluoride. The standard reduction potential is plus 2.87 volts. So we see that E0 therefore reflects the ability of the reactant to act as an oxidizing agent. Fluorine is the best oxidizing agent. So the more positive E0 is, the reactant is a better oxidizing agent. At the bottom of the table, we see group 1 metals, lithium and sodium, as examples. We see that they have very large negative standard reduction potentials. That means they're most stable in their ionized form. So the favorable reaction is the reverse of what is shown here. The ions are stable, not the metals. Therefore, more negative E0s, the product, that would be, in this case, the metal, is the better reducing agent. We can see in the middle of the series here, we have in blue the standard hydrogen electrode, 2 protons reacting with 2 electrons going to hydrogen gas, with its standard reduction potential of 0. You'll also notice about halfway down the table from the standard reduction potential is the reduction potential for water. That takes 2 moles of water with 2 electrons to produce hydrogen gas and 2 moles of hydroxide, which we'll refer to in just a moment. We can use this table to write the spontaneous redox reaction. So if we have 2 half cells and we combine them together and we want to know which way the reaction will tend to go, we can compare their standard reduction potentials. Each of the half reactions contains both a reducing agent and an oxidizing agent. The stronger oxidizing and reducing agents will react spontaneously to form the corresponding weaker reducing and oxidizing agents. The spontaneous redox reaction is the one for which E0 for the cell is greater than 0, and that occurs between an oxidizing agent and any reducing agent that lies below it in the table we just showed, that is the EMF series. So the one that lies below it has a less positive value for its E0. The oxidizing agent is the reactant from the half reaction with the more positive E0 cell. The oxidizing agent is the species that is reduced. For a spontaneous reaction to occur, the half reaction higher in the list proceeds at the cathode, and the half reaction lower in the list proceeds at the anode, or it is oxidized. We can take as an example tin 2 with tin in comparison with silver ion and silver. We see that silver has a standard reduction potential of positive 0.8 volts, whereas tin has a negative standard reduction potential of minus 0.14 volts. So first, we reverse one of the half reactions into an oxidation step so that the difference between the E0 values turns out to be more positive. So in this case, we would reverse the tin reaction. Now the way we're going to handle this and the way Silberberg will handle this is that we'll reverse the tin half reaction, but we don't change the sign. We just understand the sign reflects the standard reduction potential, not the oxidation here as written. Our next step, we multiply the half reaction so the number of electrons lost is equal to the number of electrons gained. So we need 2 electrons for our silver process to counterbalance the 2 electrons from the tin process. Note that we don't multiply E0 times 2, and there's a reason for this. E0 is a measure of potential, not potential energy. If it was delta G, we would multiply it by the coefficient. We'll explain this just a little bit later with an equation that will clarify things. Next, we add the reactions together, canceling the common species. And in this case, that'll be the electrons on both sides. And then we calculate E0 for the cell as E cathode minus E anode. And in this case, then we'll take the 0.8 minus the negative 0.14, and we see this has a cell potential of 0.94 volts. That is taking tin metal reacting with 2 moles of silver ion to produce 2 moles of silver metal and 1 mole of tin 2 ions. This is the spontaneous redox reaction. If we were to reverse the reaction, the voltage would reverse and we would have the electrolytic cell. Now, we can look and see which metals are stronger reducing agents, and we can compare these to hydrogen in the center of our table earlier. Metals that can displace hydrogen from acids are metals that are stronger reducing agents than hydrogen, or correspondingly, their ions are weaker oxidizing agents than acid. So in this case, we can look at the standard hydrogen potential, standard hydrogen reduction potential of 0, and we can compare that with iron. Iron 2 being reduced to iron has an E0 of minus 0.44 volts. That is more negative, therefore we'll reverse that reaction. So the spontaneous reaction is the one of iron metal reacting with 2 moles of acid to produce iron 2 plus hydrogen gas. The cell potential here is 0.44 volts. The lower the metal is on the list of half cell potentials, the more negative its E0 half cell, and the stronger the metal is as a reducing agent, and the weaker the metal ion is as an oxidizing agent. The more negative that E0 half cell the metal, the more positive its E0 cell for the reduction of hydrogen, and the more active a metal is. Metals that can't displace hydrogen are ones that we consider to be noble metals. And here our example we're going to use is silver. So in this case, silver metal is a weaker reducing agent than hydrogen gas. Correspondingly, silver ion is a stronger oxidizing agent than acid. And this is the reason that silver is used, sometimes silver ion is used as a disinfectant. And we can see here that the standard reduction potential for silver is positive at 0.8 volts. So if we reversed it, if we tried to take silver metal and oxidize it with acid to silver ion and hydrogen gas, the E0 cell is negative. That's negative 0.8. This is the non-spontaneous reaction. This would actually be an electrolytic cell, and we would have to drive it if we wanted to do this. So the higher the metal is on the list of the half cell potentials, or the more positive its E0, the weaker the metal is as a reducing agent, the stronger the metal ion is as an oxidizing agent. The more positive the E0 half cell of the metal, the less positive its E0 cell for the reduction of acid, and the less active the metal is. Next, we can start to think about the activity series. We learned the activity series in a non-quantitative manner back in General Chemistry 1. And we can look both at water and metal versus metal. First, we'll look at water. So metals that can displace hydrogen from water are those whose half reactions lie below that of water. Remember, water was about halfway down the series below acid. And water's standard reduction potential is minus 0.83 volts. So any metal that has a standard reduction potential more negative than negative 0.83 volts can react with water to displace hydrogen gas. An example is shown here with sodium. Sodium can go to sodium ion plus 2 electrons, and those 2 electrons can be given to water to produce hydrogen gas and hydroxide. So in this case, that electrochemical cell will have a voltage of plus 1.88 volts. It's a very favorable spontaneous reaction. We can also see if one metal can displace another. We simply see who has the larger standard reduction potential in the positive sense. We can compare zinc 2 and iron 2. Zinc 2 going to zinc metal has a standard reduction potential of minus 0.76 volts. Iron 2 going to iron has a standard reduction potential of minus 0.44 volts. Therefore, iron is more stable in the metallic form. If these two cells are in contact, zinc metal will react with the iron 2 to produce zinc 2 and iron metal. And the cell voltage, the standard cell voltage, will be 0.32 volts. Calcium is another metal that can displace hydrogen from water. Calcium gets oxidized by releasing 2 electrons. Water can take those 2 electrons and produce hydrogen gas and 2 hydroxides. Therefore, overall, if we throw calcium into water, we will produce calcium hydroxide and hydrogen gas. We've been saying that E0 that is positive is spontaneous, and E0 that's negative is non-spontaneous. We've also pointed out that E0s are not multiplied by N when we add reactions. And we'll see why this is the case in this slide. The first equation gives us an idea here. Delta G is a measure of energy. E is a measure of potential. We can think of it this way. Gravity is a measure of potential, or analogous to potential, but energy would then be a mass at a particular altitude. When we release the mass, it'll convert potential energy into kinetic energy. But without a mass, we only have an altitude. We don't have potential energy. Now, in this case then, if we have a voltage, we need to multiply by the number of electrons to figure out how much energy we have. And as chemists, when we want to know the amount of electrons, we use moles, N for moles of electrons that are transferred in a reaction. But voltage, if we multiply it by moles, doesn't give us energy. We need to multiply voltage times coulombs, which is the standard unit for charge, number of charges. So we need a constant, and this is called Faraday's constant, F, which converts between coulombs and moles. And the equation here shows us that F is equal to 9.65 times 10 to the 4th coulombs per mole. So we see that a mole is a much larger amount than a coulomb is. It takes nearly 100,000 coulombs to make 1 mole. Therefore, if we want to figure out energy from our electrochemical cell voltage, we need to multiply by minus, because minus converts from our potential space into our energy space, N, our moles of electrons, times F, which is our Faraday's constant, times the cell voltage that we've measured. Now, under standard conditions, delta G0 is minus NFE0. So delta G is minus NFE, a very important equation, and delta G0 is minus NFE0. We learned earlier in chapter 20 that delta G0 is related to equilibrium constant. Delta G0 equals minus RT log K. And that is using natural logarithms. So if we substitute in for delta G0 as minus RT log K, minus RT log K equals minus NFE, we do this simple rearrangement here. E0 equals RT over NF, natural log of K. You can convert this to base 10 logarithms if you like. 0.05916 or 0.0592 over n log k is equal to E0 cell. And we can rearrange the base 10 log times base 10 log, of the equilibrium constant is equal to n times E0 for our cell divided by 0.059. Therefore, if we know our cell potentials, we can convert them into equilibrium constants. This is an important equation. This slide then summarizes the relationship between standard free energy, standard cell potential, and equilibrium constant. The three equations that tie these together are shown here. And from the table we see for delta G zeros that are negative, the standard reaction is spontaneous, and the equilibrium constant will be greater than 1, and the standard cell potential will be greater than 0, or positive. So spontaneous reactions under standard conditions have delta G zeros that are negative, E zeros that are positive. Reactions for which the standard potential, the delta G zero, is 0 are ones that have equilibrium constants that are equal to 1. And in those cases, then E0 cell will also be equal to 0. If delta G0, the free energy under standard conditions, is positive, then the equilibrium constant is less than 1, and E0 for the cell is negative. We can take our general Gibbs equation and use this to come up with a general cell potential equation, which we call the Nernst equation. Remember earlier we learned that delta G0 plus RT natural log Q is equal to delta G, that is free energy under any set of conditions. And we can simply substitute in E's for delta G's, and we end up with the following relationship. Your book derives this equation for you, and if you want to talk about it, you can come by office hours and we can derive it there as well. So the Nernst equation tells us the cell potential under any given set of conditions is equal to the standard cell potential minus RT over NF natural log of Q. Or this can be written as E0 cell minus 0.059 over N base 10 log of Q, where Q is our reaction quotient that we've looked at earlier this semester. So it looks like the equilibrium constant, but it can be under any conditions. So whatever values we happen to have for our system away from equilibrium, we plug those in. Now, when Q is less than 1, the reactant concentration is greater than the product concentration. The natural log of Q then will be less than 0, so E for the cell will be greater than E0 for the cell. When Q is equal to 1, ln Q is 0, so we are at the standard conditions. E cell is equal to E0 for the cell. All of our concentrations are 1 in that case. When Q is greater than 1, the reactant is less than product. Natural log of Q is greater than 0, so E cell is negative, or is negative relative to E0 cell. It is less than that value. So the Nernst equation is something we'll use, and it's used throughout chemical sensor, electrochemically based chemical sensors or potentiometric sensors, and in lots of other cases. It's a very important equation. Here we see a graph that relates cell potential to concentration for our zinc-copper reaction that we've been looking at this chapter. So the spontaneous reaction is zinc metal reacts with copper ion to go to zinc 2 ion plus copper metal. The value for Q, the reaction quotient, is the zinc ion concentration divided by the copper ion concentration. The copper solid and zinc solid are both equal to 1 because they are in their standard states. So we just include the zinc and the copper ions here for our Q value. So here on our x-axis, we have that ratio zinc to copper. And then correspondingly, we have E cell on the y-axis. We're taking the log of Q along our x-axis. You can see it's a logarithmic scale. And so we have a linear relationship. When we're at the ratio of zinc to copper equals 1, that's our standard cell. So the cell voltage here is 1.1 volts. As the zinc ion concentration increases, E cell drops, becomes less positive. If the copper ion concentration goes up, the Q value goes down, so E cell goes up. And that's what's illustrated here in the table. E is greater than E0 when Q is less than 1. E is equal to 0, equal to E0 when Q is equal to 1. And then E is less than E0 when Q is greater than 1. E will equal to E0. E will equal 0 when Q is equal to K, and that's the dead cell case. So the dead cell case is when the value for Q is equal to the value for K. That's the equilibrium case. When you're at equilibrium, you can derive no energy. Now, there's a special kind of cell called a concentration cell. You can actually take the copper to copper metal half reaction and put it in both sides of your electrochemical cell. You can make it both the anode and the cathode. How does this work? Well, you simply change the concentrations between the two cells. So one cell, here, as you can see from the figure on the left-hand side, the left-hand cell has a lighter color to it. That means the copper ion concentration is lower. It's 0.1 molar copper. And then the cathode for that electrochemical cell, the right-hand cell, copper is 1 molar. So you can see that the copper concentration is lower on the left-hand side and higher on the right-hand side. So the reaction is going to proceed such that the copper is going to plate out on the right-hand electrode. So that's the cathode. That'll be the cathode relative to the other side. So these concentration cells do work, and they're used a lot of times for what we call electrochemical sensors. And one of the common cases of this is the laboratory measure of pH. What you do is you have two electrochemical cells that are both have known values, and then you put a barrier between them, and that barrier is typically a thin glass membrane, or there are some solid state crystals now that also respond to pH. And what happens is at that barrier you create a slight voltage as hydrogen ions can diffuse into or out of either the glass membrane or the solid state crystal. And as it does this, it creates a voltage, and the voltage can be measured, and that voltage is related to the pH of the cell. This is the basis of the pH electrode. It's originally developed by Arnold Beckman in California back in the 1930s for measuring acidity in orange groves. When you look at an orange, even when it's not ripe, it looks orange, and of course they're unpleasant to eat. So he wanted to be able to measure the pH, and he developed this device, and ultimately led to Beckman Scientific. There's a variety of different electrodes, not just pH electrodes. So there are electrodes that can measure potential for ammonia with ammonium, bicarbonate with carbon dioxide, fluoride, bromide, iodide, nitrate, potassium ion, protons, all sorts of things. So we've taken these potential measurements and used them to measure very important ions in a variety of samples. And if you're interested in this, you can learn a lot more about it in analytical chemistry. It's very important. Now, another place where electrochemistry is really important is in something called a battery. I guess everyone knows what batteries are. These are self-contained voltaic cells that are very often arranged in series such that their individual voltages are added. There are some that are just single cell, but there are many that are multiple cells. A primary battery is one that can't be recharged. So once the battery is dead, the cell reaction has reached equilibrium and you cannot recharge the system. If you try and recharge primary batteries, very often the reverse reaction does not occur, and very often you produce hydrogen gas or something else that's dangerous. Secondary batteries are rechargeable. Once they have reached equilibrium, they can be put into an electrolytic cell and driven backwards to restore their energy. Let's look at a series of batteries. So the first one we'll look at here, the alkaline battery, not rechargeable, and these are the ones, for example, we see in lecture halls to drive microphones, but you probably use them for a variety of purposes. They're inexpensive, they're not environmentally problematic, and they also keep a constant voltage throughout their life until they die. And they're based on the following two reactions, and the overall process is shown here. You've got zinc metal with a paste of potassium hydroxide, and that's in equilibrium with zinc oxide solid. And then our cathode is manganese 4 oxide with water, producing manganese 2 hydroxide. And if we combine this together, we see the overall cell. What's very interesting to notice here is all of the redox active species, zinc metal, manganese 4 oxide, zinc oxide, and manganese 2 hydroxide, are all solids. Therefore, as long as they're present, their concentrations are equal to 1. That's why the E cell is equal to 1.5 volts, and it does not sag during the lifetime of the battery. We'll see that for a variety of batteries that we're going to encounter next. Next up is the silver button battery. You've seen these. These are a little bit more expensive, but they can be very small and have long lifetimes. Here we got zinc as our anode. That undergoes oxidation, and the reduction occurs with silver oxide going to silver metal. There are a couple of types of lithium batteries. Here we're looking at the primary lithium battery, which is often used as a medical implant. These typically have very high energy to mass ratios, which is why they're used for implants, but they tend to not have very high current capacities. So they don't provide a large surge of current, but they'll tend to have long lifetimes because of their high energy to mass ratio. Next, we'll look at some secondary batteries. And one of the most common ones that all of us encounter is the lead acid car battery, or the lead acid battery that's used for a variety of vehicles. This is rechargeable, and it can also produce a very high current surge. So, for example, you hear 500 amps of cold cranking power. So instantaneously, or for very short periods, these batteries can produce very large current values. So these generate electrical energy when they discharge, and we can see their anode is as lead plus, it's lead and sulfuric acid. So lead plus the bisulfate produces lead 2 sulfate plus protons plus electrons. And at the cathode, we have reduction, where lead 4 oxide, that is a really good oxidizing agent, reacts with protons and bisulfate to produce lead sulfate. So you notice that the overall discharge reaction is lead 4 oxide reacts with lead to produce lead sulfate in the presence of sulfuric acid and water. And then that gives you your current surge. And then while your car is driving, you use your alternator to convert a little bit of your mechanical energy of your internal combustion engine into electrical energy, and you recharge the battery. So the lead sulfate then goes back to lead 4 oxide and lead metal. Notice here that lead on the recharge cycle lead is acting as both the oxidizing and the reducing agent. This is something we call a disproportionation reaction. And here is a schematic that shows the discharge and the recharge of the lead acid battery. So you probably have seen these and had to change these before when your car battery ultimately goes out on you. You know, on the top we see the voltaic action, that is the discharge cycle, and the discharge cycle hits when you turn over your key to start your car, and that connects you electrically through your starter. Your anode dumps out lots of electrons through the starter to kickstart the internal combustion engine and get it going. And we see that the lead in this case converts to lead sulfide and lead oxide. Lead 4 oxide is also converting to lead sulfide. And then once you get driving, you switch over and go into the electrolytic mode. And there your car engine takes a small amount of its drive and uses it to drive the lead acid cell in reverse direction to regenerate the lead and the lead 4 oxide. Here's the nickel metal hydride battery. These are in a lot of rechargeable appliances, like if you have a blower or electrical mower or electric drill that you use for portable purposes where you're away from a power supply or, away from electrical outlets. And the metal hydride batteries, the anode and cathode reactions shown are here. Typically, the metal is a lanthanide nickel alloy. And one of the issues with the nickel metal hydride batteries is they tend to spontaneously discharge, which is why you need to recharge them every time you have to go out and use them. When they sit, they tend to have pathways that allow them to discharge under quiescent conditions. One of the most common and popular batteries is the lithium-ion battery. This works a little bit differently. It works with lithium and graphite. So you have lithium intercalated into graphite. At the anode, then, the lithium is released, and you get lithium-ion plus electrons. At the cathode, you have lithium and a manganese oxide species going to LiMn2O4. Here's the overall process. This is not done in an aqueous medium, of course, because we know that lithium is a very reactive metal. The great value of lithium-ion batteries is lithium is, of course, the lightest metal that exists in the known universe. And so that means that lithium battery has a very high energy density. So it's used in lots of cases, lots of different applications. And it is a good secondary battery that can be readily discharged or recharged. One of the issues, though, is since you're not using an aqueous medium, you have an organic solvent, and there's potential for flammability. One of the other issues is the limitations on lithium. It's somewhat of a rare metal, and as more and more people use these in larger and larger abundances, lithium is becoming more scarce. Next up, we're going to look at fuel cells. Fuel cells produce energy just like a voltaic cell does, but you have to continuously supply a fuel to it in order to carry out the redox reaction. So a fuel then enters the cell and generates electricity through a controlled combustion reaction. One of the, you might think, well, why not just do a combustion reaction? It turns out that fuel cells have a much higher efficiency than internal combustion engines. You know that internal combustion engine efficiency depends on the ratio of the operating temperature to the cold reservoir temperature. And typically for automobiles, efficiency may be 25, maybe 30% for the internal combustion engine, whereas fuel cells can produce energy with much higher efficiency, easily greater than 50% in many cases. So the reaction rates are generally lower in fuel cells than in other batteries, so you have to use an electrocatalyst to speed up the reaction. And this can be done with alcohols. It can be done with other high energy organic molecules. The highest energy density combustion molecule on a mass basis, of course, is hydrogen. And so we show a hydrogen fuel cell here. Hydrogen can be oxidized at the anode to protons plus the electrons. Then the cathode, the reduction process, is taking those protons, reacting with oxygen to produce water. Thus, overall, hydrogen, and this is shown in, this is a typo here, hydrogen plus oxygen gives water. That's the correct, so there's a typo on this, and that'll be corrected in the general slides. The last type of electrochemical cell we're going to look at is one that is often considered an unintentional electrochemical cell. That is corrosion. This is the environmental voltaic cell where humans take a lot of effort and put a lot of energy into taking metal ions from nature and reducing them into metallic substances and using those metals as structural materials and for other purposes. And nature works against us in the opposite sense, taking those metals and reoxidizing them back to their ionic form. So we can think of corrosion as a process whereby metals that humans have produced for various applications are oxidized back to their oxides or sulfides or other forms. So the rusting of iron metal will be the example that we'll use. This is a common form of corrosion. So rust is not a direct product of the reaction between iron and oxygen. Turns out, iron doesn't react that fast with oxygen in its pure form. It tends to go through a series of complicated electrochemical reactions. So the rusting reaction requires water, moisture, and it happens faster when there's protons around at lower pH, when there's ionic aqueous solutions around like salt water that can help carry charge, and when oxygen is in contact with oxygen as well. So you need typically water and oxygen, and it's facilitated by ionic solutions at low pH. The process can be seen as follows. The anodic reaction, that is the pitting reaction, this is the real loss of iron reaction. That is, iron goes to iron 2 plus 2 electrons. When this happens nearby, in contact with the metal, there'll be moisture and oxygen. So our cathode, where reduction occurs, oxygen reacts with our protons to go to water, such that our overall reaction is iron plus oxygen plus protons in an aqueous solution give us iron 2 ions and water. Now, this is our electrochemical process that removes iron and causes the pitting, which is the real problem. That's the real loss of structural integrity. What we typically see is a rusting process where the iron 2 ions that are produced will actually pick up water in the presence of oxygen, get oxidized to iron 3 to form iron 3 oxide. That's the reddish material that we identify as rust. So protons are consumed in the first step. They lower the pH. They increase the overall rate of the process. They're ultimately produced during the rusting process so they can get involved in the reaction again. Therefore, protons are acting as a catalyst since they're regenerated in the second part of our process. This is, of course, a major issue and causes a very large economic impact and can also result in dangerous situations where structural iron can be weakened. If we have another metal in contact with the iron, it can speed up this electrochemical process. And in fact, you often see this if you have two metals in contact with one another, you'll see accelerated corrosion because you'll have one metal act as the cathode and one as the anode. If we put copper in contact with iron, this creates a real problem because the copper can be the inactive cathode and speed up the reaction. So this speeds up the reduction reaction of oxygen and gives us soaks up the electrons that are produced from the iron oxidation process. This can be used to our advantage. So in the presence of copper, this is a problem. And typically, if copper and iron have to be met, they'll typically put a rubber barrier or a gasket between the two so the metals do not come into contact electrically. But we can also use this as a way of keeping the iron intact. So we can put the iron in contact with zinc, and that's shown here on the right-hand side, cathodic protection. The zinc can be used to galvanize the iron. So we have galvanized iron, we'll have zinc in contact with it. The zinc then becomes a sacrificial metal. The zinc will preferentially oxidize because zinc has a larger standard reduction potential and a larger negative standard reduction potential than does iron. Its more negative standard reduction potential means that it is more readily oxidized. So as long as zinc metal is present in contact with the zinc will continue to get oxidized and the iron will remain structurally stable and not get pitted. Metals that can work this way that are most commonly used are zinc and magnesium and aluminum. These are all more active metals than iron, and they're all preferentially oxidized relative to iron. Next, we can look at electrolysis of species. So electrolysis is when we run electric current through some material, either a molten electrolyte or an aqueous solution, and the electrons will split the substance by the input of electrical energy. So during electrolysis of a pure molten salt, the cation is reduced and the anion is oxidized. A molten salt will be, for example, liquid sodium chloride. So the more easily oxidized species typically reacts at the anode, and the more easily reduced species reacts at the cathode. And if we have water as an example, we can actually run electric current through water. And if we apply a voltage larger than the cell potential for the hydrogen-oxygen system, we can see that the oxidation half reaction will take water and produce oxygen and protons. And the reduction reaction will produce hydrogen gas and hydroxide. And of course, the protons and the hydroxide can react to regenerate water. But the net process is water is split into hydrogen and oxygen. This is a very intriguing process for producing hydrogen, which is a great energetic material. It can be used to drive combustion engines. And of course, when hydrogen combusts, it produces water, which is very clean. The one issue with this reaction is it requires a larger voltage than the cell based on the Nernst equation because of an activation barrier in the chemical process. And that extra overpotential actually wastes energy. Now, when we take an aqueous salt solution, now if we take a molten salt, of course, we'll produce the metal plus the oxidized anion. So, for example, sodium chloride would produce sodium metal and chlorine gas if we take the molten sodium chloride and we apply voltage to it. And if we do this with water, we'll get hydrogen and oxygen. When we take salt, like for example sodium chloride, and dissolve it in water, then we find it's a little more complicated. The strongest oxidizing agent is the species that is reduced, the one with the most positive electrode potential. And the strongest reducing agent, that is the most negative electrode potential, is oxidized. So for example, if we take sodium chloride, aqueous solution, and we electrolyze this, we don't get sodium metal when it's reduced, we get hydrogen gas, because hydrogen gas is produced more readily from water than taking sodium ion and producing sodium metal. And you would predict this: if I throw sodium metal in water, I immediately get hydrogen gas. So sodium just remains as a spectator. So if we take brine solution and we electrolyze it, we'll get chlorine at the anode, and we get hydrogen at the cathode, and we end up with sodium hydroxide solution. This is a large industrial process for making chlorine bleach, chlorine gas, and for making sodium hydroxide. So to summarize, what we get when we do electrolysis of aqueous salt solutions, some elements can be prepared electrolytically from aqueous solutions of their salts, and that would be cations of the less active metals like silver, gold, copper, chromium, platinum, and cadmium. They're reduced to the metal. The cations of the more active metals like sodium, but the other group 1 and 2 metals as well, and aluminum, you can't produce those metals from aqueous salt solutions. The water is preferentially reduced to hydrogen, and you get hydroxide instead. In fact, making aluminum metal or sodium metal or magnesium metal requires typically high temperature. So you take the molten salt to very high temperature, and then you electrolyze those. So if you take sodium chloride and you electrolyze it, you get sodium metal. If you take magnesium chloride, this is how magnesium is produced. And of course, magnesium is used in large quantities for example, structural materials or magnesium blocks in cars. Aluminum, it can't be done simply. You have to actually take a mixture of an aluminum oxide and something called cryolite in order to do this. It's something called the Hall process, which is very interesting, and you can look that up on your own. Now, these cations being reduced, so we know that we're having reduction at the cathode. The anions that are oxidized, because of the overvoltage from oxygen, typically include like chlorine, so Cl2, or bromine, Br2, or iodine. It doesn't work for fluoride because fluoride is too reactive. But this is the process that's used to make industrially to make chlorine gas. So the anions that are not oxidized in water would be fluoride, and the oxoanions, where the central nonmetal is already in its highest oxidation state. Finally, we can look at the stoichiometry of electrolysis. If we carry out an electrolytic reaction and measure the current that flows, if we multiply the current times time, we get charge out. It says change. It should say charge. You don't get change, you get charge. So if you have charge, you can take charge and divide by Faraday's constant and get moles out. Once we have moles, we're ready to do all the stoichiometry we've been calculating all year long. So Faraday's law of electrolysis states that the amount of substance produced at each electrode is directly proportional to the quantity of charge flowing through the cell, which you would likely understand and recognize immediately. The current flowing through the cell is amount of charge per unit time. Current times time gives us charge. Charge divided by Faraday's constant gives us moles. Once we have moles, we plug into our balanced equation. Now you should be ready to work on practice problems for Chapter 21.